In this video, I'm going to talk about the factorial analysis of variance, which is yet another special case of the general linear model that allows analyzing the effect of two categorical explanatory variables on the mean of the response variable. We start again, as usual, with an exploratory data analysis to be followed by the frequentist and the Bayesian model fitting. As in previous videos, all these codes and scripts and data sets to run this analysis are in the website shown in the screen. In previous videos and in previous chapters of the book, chapters 4 and 5 and videos 5 to 8, I explained the general linear model for numerical explanatory variables and for a single categorical explanatory variables with either one or several levels. The statistical model in all cases was that the response variable y has a normal distribution whose mean, mu of y, depends on the values of the response, the explanatory variables, and also has the variance of the response variable sigma of y. In this video, this general linear model will be extended to analyze the effect of several categorical explanatory variables and their interactions on the effect of y. So let's define interaction. Interaction is when the effect of a single explanatory variable on the mean of the response variable depends on either the value or the level of another explanatory variable. That is, in this case, we don't have a simple problem, but we have a slightly more complicated problem, since whenever the interaction between explanatory variables is important or relevant, their effect on mu of y must be interpreted together and not on a separate basis. So the original statistical model for the factorial model is written as follows. Let's identify the terms in this linear equation. First, we have the global mean. Then we have the single effect of factor A. Let's imagine that there are two factors, A and B. Then we have the single effect of factor B. Then we have the interaction between factors A and B. And then, of course, as usual, sigma is the error, or that has, and by hypothesis, has a normal distribution with mean of 0 and variance of sigma square of y. There is again a decomposition of the total variation as it was explained in the previous video of the one-way analysis of variance, in the sense that there is a given amount of explained variation by the effects and interactions of the explanatory variables, and the unexplained variation associated with the error or variation around the mean. So let's use a simple example with two factors, A and B, each of which has two levels. So in this case, factor A and factor B, and as before, the statistical model estimated in R is written a slightly different way compared to the previous model, in the sense that y has a normal distribution, and we now define reference the mean of the reference level. In this case, the reference level is arises because of the combinations of the two factors A and B. In this case, would be the combinations of A1 and B1. So the estimated group means is this is the mean of A1. A1 is the mean of the reference level. The mean of A1 and B2, this one, is the mean of the reference level plus a differential. And the mean of A2, B1 is the mean of the reference level plus another differential. These are the single effects of factors A and B. Whereas the mean of the combinations A2, B2, for this we need to make one change first, another change second. These are the two changes that we make, plus the effect of the interactions. So based on this rewriting of the statistical model, we can interpret the parameters estimated when we fit the statistical models. So let's So the rewriting of the statistical model now focus on the differentials of means and on the interaction term, whose estimation is the main goal of the analysis. The estimated parameters therefore denote the magnitude of the effects of each level of each factor and their interaction on the mean of the response variable. Just as in other cases, the ANOVA tables provide the statistical significance of the simple or single level effect of the factors and of their interactions. Whenever the interaction is relevant or significant, statistically significant if you wish, the a posteriori tests need to be carried out in a slightly different way from what we saw in chapter 1 and in video 8. It's not complicated, it's just that we need to do an extra step. So let's import the data. The data concerns two explanatory variables, source and amount, and the response variable is weight. The goal is to assess whether the amount of protein affects the weight gain of rats depending on the source of protein on the diet. So we obtain a statistical descriptive statistics for each group. The group now is defined by the combination of levels of the two categorical explanatory variables, and we calculate, we use our function desc_stat descriptive statistics that takes as an argument a vector and calculates the mean, the median, the standard deviation, and the number of data points. So this is a design experiment in which we see each combinations of level beef and high, beef and low, serial high and serial low has exactly the same number of data points. From here we see that the magnitude of the difference of the mean difference comparing high and low in weight are different when the source is beef, that is plus 20.8, or compared to when the source is cereal. The difference now is 2.0. So it means that the difference between high and low depends on the level of the other explanatory variable. This is what we mean by an interaction. Of course, this is just descriptive. We need to assess it by fitting a statistical model. The interaction can be better visualized in a plot, in a box plot. In this case, the box plot, the four categories arises because of the 2x2 combinations of the explanatory variable, source and amount, and we see that just taking the mean, for instance, which is the gray square, the magnitude of the difference between the gray square between beef high and beef low is different from the magnitude of the difference between beef low and beef high. So in order to assess which is the best probability distribution to model the response variable, we compare the two usual candidates, which are normal and log normal. The fit of either distribution would probably be fine. So let's keep things simple and choose normal. So the frequentist model fitting, the statistical model is written at the right in the screen. We are going to use it when we interpreted the model fitting. The model is fitted by putting the response variable and the explanatory variables now separated by a multiplication sign. This is a shortcut in R to simply fit the single level effect of source, the single effect of amount, and their interaction. So let's see the summary of the model. The summary of the model is as follows. Let's recall first that this value, the residual standard error raised to the squared, is an estimation of the variance of the response variable. So let's have a look first on how R fits this model. In order to fit the model, R creates a model matrix with binary indicator variables that denote the parameters to be estimated. So it denotes the reference level of each of the two factors by zeros and the other level as ones. And this and I'm going to explain the common term. So the reference levels are beef and amount. So this is the mean of the response variable weight for the reference level, BIF, and amount. So now we have, so which again, this is a standard error of this mean, and this p-value says whether this mean is significantly different from 0, which is not the goal of this analysis. Now the following term, source serial, is the differential of means when we change from the reference level BIF to the other level serial while keeping the reference level of the other explanatory variable in high. So this is the difference of mean for that situation, and this tells us that the difference, this p-value tells us that that specific difference of means is statistically significant. Amount low is reflects the differential of means, which in this case negative, saying that when we change from amount high, the reference level, to amount low while keeping the reference level of source in BIF, we obtain a difference of minus 20.8 that happens to be statistically significant. So let's interpret the parameter values. Here I'm just showing the estimates and not the standard errors or p-values. I highly recommend, when interpreting this type of models involving interaction between explanatory categorical explanatory variables, to make up the following table. In the following table, we have the reference level BIF and high. This is the number 100 grams. This is the mean of the response variable. Now, if we change from BIF high, from high to low while keeping the reference level on BIF, we add this differential that happens to be negative. So this now is the mean of weight for the combination BIF and low. The difference from the reference level is minus 20.8. Now, if we switch from BIF to serial while keeping the reference level on high, we need to add the differential of minus 14.1. So 14.1 is the difference between 100 and 85.9 while keeping the reference level of the amount explanatory variable as in high. Now, if we now move from the reference levels of BIF and high to the other remaining cell in this 2x2 table, we need to add the single level effects of these switches. Going from here to here, we add the minus 14.1. Going from here to here, we add the differential of minus 20.8, and then we add the interaction between the two levels. So here the 83.9 is the mean of the combination serial amount low and source serial. I hope this is now clearer. So I highly recommend making these 2x2 tables to interpret the parameter values. So the ANOVA table gives the statistical significance of the single level effects of each of the explanatory variables and of their interaction. So whenever there is an interaction, a model has an interaction between explanatory variables, we must always start by interpreting this ANOVA table by interpreting the interaction. Whenever the interaction is statistically significant, let's assume it is, for the sake of the example, is on the margin, we must always disregard the single level effects of the explanatory variables and focus on the joint effect of these variables on the mean of the response variable. So the a posteriori comparisons, when there is an interaction between factors, need to be based on a new statistical model that combines the effect of these interacting variables. So we are creating the same data frame a single explanatory variable. Let's call it source amount, source.amount, which is a factor, and this factor arises by joining, pasting. This is joining two pieces of text of the levels of each of these explanatory variables separated by a dot. So I so these are the levels of this joint explanatory variable. Now that we have a single explanatory variable, and we feed an artificial model that is of no interest, of course, of this synthetical explanatory variable, which gives us more or less the same results that we saw before. So we can now make the following orthogonal contrast. These are contrasts that are written as follows. Let's say that we want to assess whether BIF high, the mean of the responsive variable in BIF high, is equal or not to the mean of the responsive variable in BIF low. So another way of writing this is to pass what is in the right hand side of the equation to the left, but with a negative sign, and this amounts to what we call an orthogonal contrast, because the sum equals to 0. So if we want to make the similar comparison, but for serial high versus compared with serial low, we write another orthogonal contrast. So let's assume now that we want to compare the average weight, the average of weight between BIF high and BIF low. That is, this is the average of BIF. We want to compare it with the average of serial high and low. So we are now comparing two averages, the average of BIF against the average of serial. So this is the same as to write the following equation. Let's simply recall that divided by 2 is the same as multiplying by 0.5. So we have a similar situation. We could now pass the terms of the right hand side to the left, or the terms of the left hand side to the right, and obtain an equation that where the contrast equals to 0. So this contrast, so we can write three vectors, d1, d2, and d3, and these vectors d1, d2, and d3, d1 corresponds to the contrast between high and low for BIF, d2 corresponds to the contrast between high and low for serial, and d3 corresponds to the vector for the average BIF, and average serial. This is the vector d3. We can combine these three vectors by putting them together into a matrix. The matrix is called contrast matrix, and this is just the text here in between quotes is just a piece of text to help us identify the vectors, and we put them together with the command row bind that combines three rows into a single matrix. We are going to use this matrix in a posteriori contrast, not in every possible contrast, but just in this specific contrast that are of interest for us to answer the question posed that motivated the research. So we use as before, as in the previous video for the one-way analysis of variance, we use the multcom package, but not as follows. So instead of we use the model that we just run, that has as an explanatory variable source.amount, that's the synthetic explanatory variable, and here instead of 2k that will make all the possible contrasts, we just use the that matrix written in the previous screen. We used we obtained the specific contrasts, and we correct the p-values for each of the specific contrasts. We make three specific contrasts, the ones that we want, by the false discovery rate method, and we can assess their statistical significance. Another way to represent this a posteriori contrast is by a plot in which we have the magnitude of the mean difference and their 95% confidence intervals. So this orthogonal contrast allows us to only make the comparisons that we judge to be relevant to answer the question, avoiding the brute force approach involving all possible comparisons. This will become far more interesting whenever we had explanatory variables with 3, 4, or more levels, and their combinations will increase very fast. So we use The package room allows us to gather the input for the residual analysis. As usual and before, I will not reiterate the explanation, and with this we make the following plots. We have the standard residuals against the fitted values, the standard residuals against the combinations of the two explanatory variables. So now see more or less a random scatter. Of course, we can identify 4 groups. We obviously have 4 groups in this data set. And so, but we see that the spread of the residuals in the positive side for each of the group is very similar to the spread of the residuals for the negative side. We now see that in the plot B that the median of the residuals is very similar among the groups and close to 0, as it should when a model fits well, and the variation of the residuals taken as the width of each of these boxes is pretty similar, suggesting that the residuals have a very similar variation. Plot C shows that the residuals follow a normal distribution as they should, and plot D shows that there are several points with similar Cook distances, not suggesting that we should worry too much about any of them. So overall, the model has a very good fit to the data. So we can communicate the results as usual with a table with parameter estimates and the 95% confidence intervals, and even better with the conditional curve obtained with the package GGFX. We obtain the predicted values for each of these 2 explanatory variables with the original M4 model that yields a very simple data frame in which we have for the 4 predicted values of the means under 95% confidence interval, from which we can make the following plot. The fact that these 2 lines are not parallel is an indication that there is a relevant interaction between these 2 explanatory variables. The Bayesian model fitting, we start by recalling the statistical model that has 5 parameters, meaning 1, 2, 3, 4, and 5 parameters. We enter the model into the command get prior of the package VRMS to have an idea of what priors we need to define for the models. We see that based on the previous explanation, I don't think there is any need to recall again the meaning of these parameters. We have the intercept, which is the mean of the response variable for the reference, the combinations of reference levels, and sigma, the standard deviation, not the variance of the response variable. So I set up the following priors that are best explained in terms of a plot. The priors, here I defined the mean of the reference level is an asymmetric distribution. This is why I use the log normal distribution, and I more or less calibrated the standard deviation of this log normal distribution to include ranges of plausible parameter values that could be obtained. So I also use a normal distribution for the mean of for the parameters reflecting the type B parameters reflecting the difference of means and their interactions, showing that I expect on average to have no effect, and I expect negative and positive values with the same probability. And as for the variance of the standard deviation of the response variables, I use a Cauchy distribution, which is has the same shape of a normal distribution but with thicker tails. That here ranges between 10 and 40. The model is fitted with this with the similar syntaxes as we used before, using priors, using as priors the priors that we defined in the previous distribution. And in this model, we first have the part of the output that is related to the marginal posterior distribution of each of the model parameters, and the part of the model that is related to the convergence of the chains. So we see that the convergence of the chains is would seem pretty good, since the R hat statistic is very high, is equal to 1, and the effective sample sizes are all very high. The model explains 19% of the variation of the response variable. So the interpretations of the model parameters is the same as the one obtained as the one explained in the for the frequentist fitting of this model. So the chains appear to have converged. So let's look at their posterior distributions, and indeed the three chains seem to have seem to converge to a common marginal posterior distribution for each parameter. All the chains have a very good degree of mixing. That is, they explored the same range of parameter values for each of these parameters without getting stuck in any part in a specific range for any significant number of iterations. And the parameter values for each of these chains are all nearly statistically independent. Notice that the magnitude of the autocorrelations for values separated between 1 and 20 is pretty small, less than 0.1 by absolute magnitude. Recalling the statistical model, we can fit the prior distributions and the posterior distributions to see the difference between them. And the difference between the prior and the posterior distribution reflects the information contained in the data. Let's not focus on the height of these density probabilities, but rather on the range that is that either the prior or the posterior provide support. So the shift from the prior to this posterior distribution is due to the amount of information contained in the data. This is also shown in the for each of these parameters, the 5 parameters of this statistical model. So in order to assess the goodness of fit, we use the Pearson residuals and the fitted values. This was explained before and will not be repeated again, from which we obtain the following plots. We obtain the residuals and the fitted values. Then the plot of the residuals against the fitted values, we see a more or less random scatter of the points with very similar, not identical, but very similar scatter in the positive side and negative side, except for perhaps 4 points. Here the variation of the residuals against the combinations of the two explanatory variables is less adequate, let's say it that way, than before, because there is a difference in the median of the residuals for one of the groups compared to the other groups. The residuals seem to have a normal distribution. So overall, we could say that the model has a reasonable, or perhaps, if we are generous, good fit to the data, without this degree of fitting being excellent by any means. Communicate the results. We obtain the conditional effects plot, in which we show the predicted mean of the response variables and the 95% credible intervals for each of these 4 combinations of the 2 explanatory variables. And we can also show the credible means and the 95% credible intervals of all model parameters, as usual. So this concludes this video, in which I explained the factorial analysis of variance. Further details can be seen in the book. This is just an illustration of a shortcut, if you wish, for reading the corresponding chapter. We did an explanatory data analysis, the frequencies model fitting, and the Bayesian fitting, and the codes are all here. I thank you for your attention, and I hope this was of interest to you and entices you to read either this book or any book showing this type of analysis. Thank you.